Good evening, everyone. Welcome to the 12th week of the live interactive sessions for the course on concrete technology. I am Sedu Vinayagam, a PhD scholar in the Department of Civil Engineering at IIT Madras. Okay, so we'll start with an overview of the concepts that were covered in the lectures for week 12. Okay, so this week 12 had 4 lectures. So this week was also focused on special concretes, right? So in lecture 38, we continued with the discussion on self-compacting concrete. So in particular, we were looking at different tests for judging the quality of the self-compacting concrete, right? So we are looking at different tests for, flowability, workability, and so on. And then we were also introduced to fiber reinforced concrete towards the end of this lecture. And in lecture 39, we continued with the basic theories related to fiber reinforced concrete, right? So with respect to, the orientation and alignment of the fibers, how it affects the properties, how it improves the properties of concrete. And we also looked at the different efficiency factors and also, how crack spacings are affected in the fiber reinforced concrete. In the third lecture, we continued with looking at fiber reinforced concrete. So in particular, we are looking at the strain at failure, how the ultimate strength is affected, also different properties, durability, workability, and so on, and also different types of failures like due to short fibers, pull-out failures, and also how the moment of modulus of rupture and so on is affected. And in the final lecture, we are looking at some other types, special types, some like polymer concrete, heavy concrete, and geosynthetic concrete. And then we finally concluded with aspect of sustainability. How we're looking at specifically green concrete and what can we do to improve the sustainability of concrete. Okay, so with that overview, now we'll look at some questions related to these concepts. Okay, so the first question is, dash test is effective in judging whether concrete has sufficient self-compactability. So we have 4 options. The first one is J-ring test, fill box test, T50 test, and YouTube test. Okay, I'll create a poll and you can answer in the poll. Okay, I have launched a poll. So once you are ready, you can put your answers in the poll. Okay, we have two votes so far, one for option A, one for option B. Okay, any other answer? Okay, now let us take a look at the right option. Okay, two votes for option B, one for option A. All right. So the right option is actually option D. It is the YouTube test. Okay, so here we are talking about the test for self-compactability, right? So in the first lecture of week 12, we looked at several tests for self-compacting concrete. So these are some of them, and so different tests are for different properties. Okay, so the J-ring test and the Philbox test are actually designed for testing the passability, right? So when you have certain obstacles on the path, like for example, when you place the concrete, you will have reinforcements, right? So that is an obstacle for the flowing for the flow of the concrete. So in that case, how does it pass through those obstacles? So for those for testing that, you will use the J-ring test and the Philbox test, right? So the T50 test is for the flow of slump, right? For testing that, it is the YouTube test which we use for testing the compactability, right? So and it is only for sufficient only for testing the compactability and not for the other factors. So what happens in the YouTube test? So you will have a tube in the shape of an U, right? So you'll so it will be partitioned into two compartments. So in the middle you will have a partition and there will be a gate at the bottom. So on one side you will fill your concrete to the full length of the tube, and then the gate will be initially closed. Then after some time we'll open the gate, and what happens once you open the gate, the concrete will try to fill the other side of the tube, right? So if it has sufficient compactability, so what should happen is that the height it fills on the other side of the tube, it should be almost the same as the height on the left hand side, right? So if that is the case, then you can say that it has sufficient compactability. But if it is too low, like this, then in that case you will say that it is not it doesn't have sufficient compactability, right? So that's how the YouTube test works. So this is the test that we use to test for the self compactability of SCC. Yes. So we'll move on. Question number 2 now. So the orientation of the fiber relative to the plane of a crack in concrete influences the reinforcing capacity of the fiber. The maximum benefit can be expected when fibers are, so we have four options: unidirectional and parallel to the applied load, unidirectional and perpendicular to the applied load. Option C is randomly oriented in 3 dimension. Option D is none of these. Okay, we have one vote for B, one vote for C. Any other answers? Okay, so let's take a look at the answer now. The right option is option A. It is, the reinforcing capacity is maximum when you have unidirectional and parallel orientation of the fibers, which is parallel to the applied load, right? So we looked at, right? So initially we started with our discussion about fiber reinforced concrete. So we looked at an ideal case. So suppose when we have a concrete, right, and we have fibers, along the length of the concrete like this, something like this, okay, and then when you apply load, right, suppose you apply tension, right, something like this. So in when you have such a configuration, when the applied load and the fibers are parallel to each other, in that case you will have the higher load carrying capacity. So this was the ideal case, but in reality you will not have fibers throughout the length, and also not all aligned parallelly to the load, right? So in reality what you will have is short fibers randomly oriented like this. So what happens is that in that case, it will not be as effective as in this particular case, right? So in this case, we also showed that when we derived it, the modulus of elasticity of your concrete, containing fiber will be, it will be EF. So VF is the volume fraction of your fiber into the modulus of elasticity of the fiber plus EM into 1 minus VF. The rest of the volume will be the mortar and the modulus of elasticity of the mortar. That is in the ideal case, right? So in general we'll have the fibers which have a higher elasticity modulus compared to your mortar, right? So this will be that will be in the ideal case. But when you have the short and randomly oriented, so you'll this first term will be multiplied by two factors, the length and the orientation efficiency factors, right? So on these factors for short and randomly oriented will be smaller than 1. So you will have the effective modulus will be reduced, right? So in this case we are asking about when it will be maximum, right? So the maximum benefit, so when these two factors are 1, right? So that is in the ideal case. So that is when unidirectional and parallel fibers to the applied load. So the right option is A. Okay, question number 3 is the workability of fiber reinforced concrete mixes dash as the fiber content dash and as the aspect ratio dash, right? So we want what happens to the workability depending on the fiber content and the aspect ratio. So the options are the workability increases when fiber content decreases and aspect ratio increases. Option B is decreases, increases, increases. C, all the three decreases, and D is decreases, increases, and decreases. Okay, the poll is launched. We have only one vote so far for option B. Any other answer? Okay, we have a couple of votes for option B and one for option C. Let's take a look at the answer now. Okay, the right option is B. So the workability will decrease when your fiber content increases and also the aspect ratio increases. Okay, so we had this chart in the lecture, so which was explaining this concept. So on the y-axis we have the VB time. So the VB time tells us how is a measure of the workability, right? So it's one of the measures that tells us how workable the concrete is. So lower is your VB time, higher is your workability, right? And on the x-axis we have the percentage content of fibers, so by weight and by volume. So and then that there are different lines, so each line represents one particular aspect ratio, right? So as what is aspect ratio? It is the ratio of the length dimension to the depth dimension, right? So the thickness, the length to the thickness, so that ratio is your aspect ratio. So we have different curves for different aspect ratios, and it shows how the workability varies as your fiber content varies. So what we see is that for every aspect ratio, as the percentage content of the fiber increases, your VB time is becoming larger, right? So that is the trend that we are seeing, right? So when VB time becomes larger, what does it mean? Workability is reducing, right? It is less workable. So higher the content of your fiber, lesser is your workability, or higher is the VB time, right? So that is for the percentage content of fiber. So that is the first and second part. So it will decrease when workability decreases when the fiber content increases. The other question was what happens with the aspect ratio, right? So if you look at it, so we have different aspect ratios here: 253, 152, and so on up to 66. So you pick any one percentage content of fiber. So for any given percentage content of fiber, so if you go up, so what do you see? So the curve on the bottom corresponds to an aspect ratio of 66, and the next one corresponds to 73, and the third one for 100. So what we see, as we go up, the aspect ratio is increasing. So what we see is that for a given percentage content, for different aspect ratios, as the aspect ratio increases, your VB time is also increasing. So it means that higher aspect ratio will give you lesser workability, right? So therefore this third part is also the workability will decrease when your aspect ratio increases, right? So that is the right option. So workability of the fiber reinforced concrete mix will be decreasing when the fiber content increases and the aspect ratio also increases, right? So that is the right option. So question number 4 is the ratio of the height of concrete in the vertical face to the height of the fill should be a minimum of dash for SCC in the L box test. So the options are 0.4, 0.6, 0.8, and 1. Okay, we have one vote for option A, one for option D. Okay, any other answers? All right. Let's take a look at the right option. Okay, the right answer is option C. It should be a minimum of 0.8. Okay, so what is this test? This is the L box test, right? So what does this L box test for? It is for measuring the segregation resistance of your self-compacting concrete. Right? So what is the segregation resistance? So you have different components, co-segregate, paste, water, and so on. Right? So segregation means it is the separation of your concrete into these individual components. So if it separates into these different components, you say that it has segregated. So this say, but you do not want that to happen, right? It should be homogeneous. Anywhere within the concrete you take, all the components should be present in the same proportions, right? So that's how you want it. So this test will measure how resistant your self-compacting concrete is to this segregation. So what we have in this L box test, so it will, as the name suggests, the apparatus is in the shape of a L, right? So you have a vertical part and then this horizontal part. So what we do is we fill this vertical face with the concrete, to the full height, and then what we do is initially again there will be uh, a gate here as we saw in the previous test. So there will be a gate here, and then there will be some obstacles here, some reinforcements here. And so what we do after filling this vertical part, we wait for a minute or so, and then we remove the gate. So what happens then, whatever is in this vertical phase, so it will start filling up this horizontal phase of your apparatus. So what happens is if it is not segregating, so in that case what we expect is that this height of this particular portion, it should be filled completely. So that is in the ideal case, right? So and then what will happen in that case is so the height on this part will be the same as the height on what is remaining here, right? So the height here, right side is called h2 and the height on the left side is called h1. So the ratio of h2 to h1, so that is the factor that we are looking at. So if that is equal to 1, so that is the ideal case. It is perfect, right? So that is in the ideal scenario. But what happens is it will not usually filling the whole height. So there will be some void. So it will be somewhat lesser than that. So that is h2, and the h1 will be somewhat higher, right? So h2 to h1 will be less than or equal to 1. So but if it has good segregation resistance, then this factor should be at least 0.8. So the minimum value should be at least 0.8. So if it is greater than 0.8, we say that it has sufficient segregation resistance, right? So if it is less than that, we say that it is not enough, it is segregating. Okay, so that is the L box test. So the threshold is 0.8 for the height h2 to h1. Okay, question number 5 is the modulus of elasticity of SCC may be slightly dash than non-SCC. So the options are higher, equal, lower, and there is no such relationship. Okay, so we have three votes all for option A. All right, so let's take a look at the answer. Right option is actually C, that it will be lower than your non-SCC. For self-compacting concrete, modulus of elasticity will be slightly lower than the conventional concrete. So why is that? So it is because of how the relative content of your aggregate and your paste. So in your self-compacting concrete, you will have a higher paste content relative to your coarse aggregate when you compare it with conventional concrete, right? So there will be higher paste content. Why? Because in self-compacting concrete, we want higher flowability or higher workability, right? So it should flow more easily than your conventional concrete, because then only it will be able to achieve cell compaction, right? So if you have higher aggregate content, your flowability will reduce, right? So because aggregate is the or the coarse aggregate is the least flowable of all the different components in your concrete, right? So we reduce that content in self-compacting concrete. So this has an effect on your modulus of elasticity. So if you remember, when we in one of the previous modules, we looked at how the aggregate content affects your strength of the concrete, right? So if you look at it in a conventional concrete, normal concrete, the highest modulus of elasticity among the different components is for the aggregates, right? So if you look at the stress strain relationship, so the modulus of elasticity of aggregate will be something like that, and for your paste it will be somewhat lower, right? So the aggregate is the strongest component of out of the different phases in your concrete, right? So when you reduce your modulus of when you reduce your coarse aggregate content, so what will happen? It will and increase your paste content. So your concrete modulus of elasticity will also come down, right? So it will be always in between, because concrete is a mix of your aggregate and your paste. So your concrete modulus of elasticity will be somewhere in the middle, right? So now when you are bringing your coarse aggregate content down and increasing your paste content, so that will have an effect on your concrete's modulus of elasticity. So this will also finally come down, right? So because your aggregate coarse aggregate content is coming down. So all this is with respect to using normal concrete. We are not talking about high strength concrete in this case, in which case the paste content, the paste strength will also be higher, right? So but here we are talking about the normal concrete. So in that case, aggregate will have the highest elasticity. So therefore, yeah, for your self-compacting concrete, so the modulus of elasticity will be lower than the non-self-compacting concrete, right? So the right option is C. Question number 6 is we have to match. So we are given with the different orientations of fiber in fiber concrete, and also different factors for the orientation efficiency. Okay, so we have orientations as aligned, 3D random, and 2D random in plane, and also the efficiency factors as 1 by 3 or 3 by 8, 1 by 6 or 1 by 5. So we have to match the right factors to the right orientation. So the options are A is matched with 1, B with 2, C with 3, A with 2, B with 3, C with 1, A3, B2, C1, and A2, B1, and C3. We have two votes so far for option B. Any other answers? Okay, so let's take a look at the answer now. Okay, so right option is option B. So A is matched with 2, B with 3, and C with 1. Right? What is that? So A, in the case of aligned fibers, so the factor, the orientation efficiency is 1. For the 3D random case, it is 1 by 6 or 1 by 5, and in the 2D random case, it is 1 by 3 or 3 by 8. Right? So that's what we saw for the orientation efficiency factor eta 0. Right? So you need not remember the actual values. Relatively you can remember what happens in each of these cases. Right? So we saw that your concrete's modulus of elasticity um, is related using the eta L and eta O for orientation efficiency into your fiber's modulus of elasticity into its volume and so on, right? So it is the product of these two factors, that will govern the final value. So we saw that when it is unidirectional and parallel to the load, right? So that is our aligned case, right? So that is when your reinforcing capacity is maximum, right? So that's what we saw in the I think the first question, right? So for that to happen, what should happen is this factor, the product of these two terms, should be maximum, right? So the maximum value for this factor is 1, right? So that's when you'll get the maximum efficiency. So for that to happen, this factor eta 0 should be 1. So that is the maximum possible value. So that is matched. So you can understand it in that way. So the second is it will be maximum in the next case is when it is random in the 2 dimension, right? So not in 3. So when it is random in the 2 dimension, it will have the next highest efficiency. So among the two, the next highest efficiency is 1 by 3 or 3 by 8, right? So that is the second match. And the third case is when it is completely random in 3 dimensions. So in that case, you'll have the least efficiency. So that is 1 by 6 or 1 by 5, right? So you can look at the relative values and then you can match the orientation factors. So that matching A with 2, B with 3 and C with 1. So that is given in option B. So that is the right match. Okay, so question number 7 is the cement based paste content is more elevated in the case of SCC than conventional concrete. So we have to say whether the statement is true or false. Okay, we have two votes for false, one for true. Okay, the right option is, it is a true statement. It's correct. The given statement is correct. Right. So what is it? So it says that the cement-based base content is more elevated in the case of SCC than conventional concrete. So I think we saw this earlier, right? So elevated means higher. So for the base content in SCC, so this is greater than the base content in normal concrete. So this is the statement. So this statement is correct. So we saw that in the case, in the question of modulus of elasticity, right? So we saw the reason for the higher or the lower modulus of elasticity in SCC is because of this relationship, right? So the base content is higher in the case of SCC than the conventional concrete. Why? Because we want improved workability and flowability. So therefore, the base content will be higher and the core segregate content will be lower, right? So we saw this. So if you look at typical mix proportions, you will have the typical total powder content would be around 400 to 600 kilogram per cubic meter, whereas the core segregate content will be much lower than in the case of conventional concrete. It will be only 28 to 35%. This is lower than what you will see in conventional concrete mix, right? So therefore, the given statement is correct, saying the cement-based base content is more elevated in SCC than conventional concrete, right? So therefore, the right option is A. Okay, question number 8 is select the factors which affect the properties of FRC. So FRC stands for fiber reinforced concrete. So the options are A, aspect ratio of the fiber. Option B is orientation of the fiber. Option C is relative fiber matrix stiffness, and option D is all of these. Okay, so we have all three votes for option D, all of these. The right option is also option D. It is all of these factors, the A, B, and C, which affect the properties of fiber reinforced concrete. So here we are not talking about any specific property. It could affect any of the properties, right? So whether or not these factors affect some property of the fiber reinforced concrete, right? So that is the question. So we saw that aspect ratio does affect one of the properties, which is it is the workability, right? So we saw how what was the relationship. So higher was your aspect ratio, lower was your workability, right? So higher, that is how your aspect ratio affects your workability. So the second is orientation of the fiber. So orientation of the fiber, again we saw this affects the stiffness of your the fiber reinforced concrete itself, right? So we saw the relationships, right? So EC is related to the orientation and also the length, right? So we saw eta naught, eta L, here fibers modulus of elasticity into the volume fraction plus the same thing for your matrix, right? So this is fibers volume, right? So the orientation does affect, right? So it is when it is aligned, and also so which is it's all parallel to the load and also in the same direction. So that orientation will give you the maximum load carrying capacity. So the orientation does affect. So B also is a factor which affects, and C is the relative fiber matrix stiffness, right? So again, when you have the strength of your fiber is itself larger, so your concrete will also have a better strength, right? So the fiber matrix stiffness will also matter when it comes to the load carrying capacity. So all these three factors affect some property of the fiber reinforced concrete. So therefore the right option is D, it is all of these. Okay, so question number 9 is, after the failure of the concrete matrix, if the volume of the fiber is higher than the critical fiber content, the concrete will be able to sustain the load. Is this statement true or false? We have two votes for false. Any other answer? Okay, so let's take a look at the answer now. Okay, right answer is actually this. The statement given is true. So what it says is after the concrete matrix has failed, if you have the fiber volume in the concrete that is higher than the critical fiber content, then the concrete will still be able to sustain the load that is applied. Right. So before we understand why it is true or false, so we need to know what is this critical fiber content. Right. So if you remember, so we looked at the relationship between the strength and the fiber volume. Right. So this is in as a fraction to the total volume of your concrete. So it's between 0 and 1. So this blue line is your fiber reinforced concrete. So you have some proportion with concrete and some proportion, the remaining proportion with fiber, right? And this black line represents, only fiber, right? So therefore you see the load carried, or the strength is the stress multiplied by the volume, right? So in this case, you have both fiber in the blue line, you have both fiber as well as the mortar. So it is so the load carried by the fiber and the load carried by the mortar. So when you look at the variation in the strength with the fiber volume, what you will see is that there will be one particular volume of the fiber, so, right? So at which point the strength of your fiber reinforced concrete and then the pure fiber, they will be the same, right? So at that volume is what we call as a critical volume. So higher than the critical volume, when you have fiber, the pure fiber case, so it can carry more strength than your fiber reinforced concrete. Why? Because is because the fiber is generally has a higher modulus of elasticity than your mortar, right? So after this critical volume, the fiber can take more load than your fiber reinforced concrete. So in this question, so we are concerned about this particular region, right? So where our fiber content is higher than the critical volume, right? So this is the part that we are looking at. So we have higher fiber content in our concrete than this critical volume. So in that case, because you are greater than this critical volume, which means that any load that is greater than this particular strength, so this is the maximum that your motor can take. So after this point, higher load, it will the motor will fail. But the fiber content that you have, which is greater than this critical volume, it can still take the load, right? So the load coming onto your fiber will be higher, and that will now sustain the load, right? So even though your mortar has failed, your fiber will now be able to take the load because you have more fiber content that than it is than the critical volume, right? So therefore, the given statement is true that in this region you can take more load because of this because you're having volume greater than the critical volume. Therefore, the right option is A, true. Okay, question 10 is dash concrete is used as a radiation shielding material in nuclear reactor cores. What is the type of concrete that is used in the radiation shielding as a radiation shielding material in the nuclear reactor cores? Okay, for this we won't have a poll. You can make use of the chat box for answering this question. The type, it's a special concrete type. So what is that type of concrete? one answer so far. Ultra high performance concrete. Any other answers? Okay, any other answers? All right, we'll take a look at the answer now. Yeah, so we have one more answer, heavy concrete. So the right option is that it is heavy concrete. So that is what we use for shielding as a shielding material in nuclear reactor cores. So we looked at several types of special concretes, right? So the heavy concrete was one such special concrete, right? So what happens? So what's the concern here in the nuclear reactor core is we want, so there will be gamma rays, right? So gamma rays and neutrons that will be emerging from your nuclear reactor core, right? So but because these are harmful, so we need to be able to shield these rays. We should make sure that these rays do not penetrate our whatever is the confinement that we are creating, right? So for this we'll make use of the heavy concrete. So what is this heavy concrete? So heavy concrete is one type of concrete where we'll use aggregates such as hematite, so which are heavy aggregates that will give you better resistance to this X-ray and the photon rays from penetrating it, right? So suppose you have something like this, so you have some photons that is impacting your heavy concrete. So what it will do, it will attenuate. Attenuate means it will reduce its penetration through it, and what is penetrating through it will be some smaller quantity, right? So if this is within your allowable limits, then it is fine. So for this purpose we use the heavy concrete, right? So heavy concrete is the right answer. So question number 11 is the application of OPC clinkers in cement production should be minimized to reduce the carbon emissions. So is this statement true or false? I'll create a poll for this one. Yeah, and one more thing that I wanted to say is one of the answers given for the previous one was ultra high performance concrete. So ultra high performance, when we say ultra high performance, it is somewhat generic, right? It's not related to any one specific property, right? So when we say performance, performance could be characterized based on different properties. Say ultra high performance for one application could be to have higher workability. So in that case, the concrete which gives you higher workability is highly performing, right? For a different application, there will be different criteria, and the one that performs better in that criteria would be giving you higher performance. So when we say ultra high performance, it is generic, and then it will be depending upon the application that we are using, right? So that's why ultra high performance is not specific or not correct for that particular application. Here we have two votes, each one for true and one for false. Right, so we have three votes for true, one vote for false. So the right option is the given statement is true. Right, so what is the statement saying is that to reduce the carbon emissions, so we have to minimize the OPC clinker production. Right, so when you are producing cement, OPC clinker should be minimized so that we have reduced carbon emissions. So this is true. Why? Because when we look at the production of cement, it is the clinker production process in our OPC, ordinary Portland cement. So that will lead to a lot of CO2 emissions, right? So if you look at it, among all our anthropogenic emissions, which means human related, human created emissions, so fossil fuel burning is the first one. So that creates the number one quantity of CO2 emissions. So second to that is the manufacturing of OPC. So you can think about the scale of the emissions that we are talking about. It contributes to 5 to 10%. So when you want to reduce carbon emissions, so this is one important concern, right? So we can reduce that by reducing the clinker production, right? So when we minimize the clinker production, so automatically directly we will be reducing the carbon emissions, because this is the one of the major contributors to our carbon emissions, right? So therefore, from the sustainability standpoint, to reduce the carbon emissions, we have to minimize clinker production. So therefore, the given statement is true. So the right option is A. Okay, so question number 12 is we have to match test different tests with the right property that we are trying to determine. So we have Punke test, Marble test, and mini slum test, and packing density, SP dosage, and viscosity modifier. Okay, so the matchings given are 1 with B, 2C, 3A, 1C, 2B, 3A, 1A, 2C, 3B, and 1A, 2B, and 3C. So which test is used for determining which quantity? We have two votes for option A and one for option B. Any other answer? All right, so let's take a look at the answer now. So the right option is option C, so where 1 is matched with A, 2 with C, and 3 with B. Okay, so what is that? So Punt-K test is for determining the packing density. Marble test is for determining the viscosity modifier, and mini slump test is for SP dosage, right? So that is the right matching. So we saw this when we looked at the mixed proportioning. So the packing density. So for this we use the Punt-K test. So it is basically looking at the voids at saturation. So voids related to porosity. Porosity is related to packing density. So you'll get it from the Punt-K test. And SP dosage, it is from the mini slump test, right? So what is SP? SP is a super plasticizer, right? So super plasticizer, when do we use it? When we want to reduce our water content, but still want to have a higher workability, right? So that's when we go for SP test. So because this is related to the workability, so you can go for determining the slump. So the mini slump test is one such test, so which can tell us what should be the optimum SP superplasticizer dosage. And for viscosity modifier addition, so we can use the marble test. So therefore that is the right matching. So 1 with A, 2 with C, and 3 with B. So that is given in option C. All right, so question number 13, an assertion and reason. So we'll be given with two statements, right? So we have to say whether assertion is true and whether reason is true, and also whether the given reason is the correct one for the given statement in assertion. Okay, so the assertion is replacing ordinary Portland cement OPC clinker with pozzolanic additives makes OPC sustainable. And the reason given is OPC clinker is ground along with gypsum for set control properties. The options are assertion and reason are true, and reason is the correct explanation of assertion. Option B is assertion and reason are true, but reason is not the correct explanation of assertion. And option C is both assertion is true, but the reason is false. And option D is both assertion and reason are false. Okay, so we have 4 votes, 3 for option B and 1 for option A. Okay, so the right option is, it is option B, that assertion and reason are true, but the given reason is not the correct explanation of the assertion. Okay, so let's look at them individually as statements. So what is the assertion? So it is replacing ordinary Portland cement clinker with pozzolanic additives makes OPC sustainable. So this is a correct statement, right? So we saw earlier, so when we looked at green concrete, so we want to reduce the OPC clinker production, right? We want to minimize it because it has higher carbon emissions, right? So when we are talking about sustainability, we want to reduce carbon emissions. So therefore, by as an alternative, we want to reduce this OPC clinker. Therefore, we increase the addition of pozzolanic materials, right? Pozzolanic materials will give you has also cementitious properties, right? So therefore, by replacing the OPC clinker with pozzolanic additives, so we still retain the cementitious properties but reducing carbon emissions, right? So therefore, that will make it sustainable. So therefore, the given statement is true. So the second statement is that OPC clinker is ground along with gypsum for set control properties. So this is also true. So if you remember the cement production process, so when we are making after the cement clinker is made, so it is ground with gypsum for the set control properties, which means that when you add gypsum, the setting time will be delayed, right? So because we don't want it immediately to set, so because we want to mix it and place it, so until then, it should not set immediately. So therefore, for controlling the setting properties, so we add some gypsum, right? So that is also true. Adding gypsum is done for controlling the set properties. So that statement is also true. So the options could be A and B, but now we have to say whether this reason is correct or not. So how do we do that? So in two, we are talking about addition of gypsum for controlling the setting property. But in one, we are talking about, replacing clinker with pozzolanic material, from the sustainability standpoint, right? So these two are totally unrelated, as we can see. It is very obvious, right? Because set property has got nothing to do with your sustainability or your pozzolanic material addition to clinker, right? So therefore, the reason is not explaining why assertion is true, right? So therefore, the right option is B, that both the statements are true, but the reasoning is not correct, is not an explanation given for the assertion, right? So therefore, B is the right option. Okay, so question number 14. Which component has lower content in self-compacting concrete as compared to conventional concrete? So the options are fine aggregate content, coarse aggregate content, paste content, and none of these. We have one vote for each for A, B, and D. Okay, two votes for B, one for A, one for D. Right. So the right option is, it is option B, the course aggregate content. I think we have already talked about this part in a couple of questions before, right? So what is the relative content of the different components in self-compacting concrete when you compare it with the conventional concrete, right? So we saw that the base content is for SCC, it is higher, right? So it is greater than your base content in a normal concrete, right? So this is what we saw earlier. And so when your base content is going up, so your coarse aggregate content will be coming down, right? So paste is increasing and coarse aggregate is decreasing, right? So paste also contains your fine aggregates. So base content and fine aggregate content will be higher, but your coarse aggregate content will be lower. This is all higher and lower. All we are saying, relatively, right? So when you're comparing it with what is your typical conventional concrete mix proportions, so relatively it will be lower in for the coarse aggregates, whereas paste content and fine aggregate will be higher, right? So here we are talking about which component has a lower content. So lower content will be for option B, coarse aggregates, right? So therefore B is the right option. Okay, question 15. So we are given with four statements and we have to say which of those four statements are correct. So the first statement is higher slump flow in SCC requires more paste. Statement 2, casting using SCC requires more labor as compared to conventional concrete. Statement 3 is the value of modulus of elasticity is found to be the same for SCC and conventional normal strength concrete. Statement 4, L-box test is used to measure the segregation resistance in SCC. So the options are 1 and 2 are true, 2 and 4 are true, 2 and 3 are true, and 1 and 4 are true. Okay, so we have two votes for option B and two for option D. Okay, the right option is actually it is D, that statements 1 and 4 are true. Okay, so we'll look at each of these statements. So statement 1 is higher slump flow in SCC requires more paste, right? So we have discussed this multiple times now. So in SCC we want higher flow, right? So and for that, so paste out of the different components, paste flows higher, flows better, than your relatively than your coarse aggregate. So we increase the paste content in SCC, right? So therefore the given statement is true. For higher slump flow, more paste is required. So in the case of self-compacting concrete. Statement 2 is casting using SCC requires more labor as compared to conventional concrete. So this statement is incorrect. So why? Because so as the name suggests, SCC stands for self-compacting concrete, which means that you don't need any external compaction to be performed, right? So that is the idea of using SCC, right, in the first place. So you don't need any external vibration compaction to be performed, right? It will fill your formwork by itself, right? So you don't need external vibration to improve your compaction. So therefore, so what does that mean? It means that because you are not going to perform external compaction, you will reduce your labor requirement, right, from this particular aspect for the casting. right? So therefore you'll have lesser labor than when you are using conventional concrete, right? So but this statement is saying the opposite of it, so therefore this is an incorrect statement. Statement 3 is the value of modulus of elasticity is found to be the same for SCC and conventional normal strength concrete. So this is also incorrect. Again, we saw this earlier. So it is actually not same, but for SCC it will be slightly lower, right? So that's what we saw. That is because it is related to statement 1 because it has more paste content, and here we are talking about normal strength concrete. Normal strength concrete aggregate has generally has higher modulus of elasticity. Therefore, when you look at SCC, because it has higher base content, its modulus of elasticity will be lower in comparison to conventional concrete. So therefore, this statement is also incorrect. And statement 4, L box test is used to measure the segregation resistance in SCC. Correct. We saw L box test, how it is done and what it is used for. It is used for measuring the segregation resistance. So that is also correct. So the right option is 1 and 4 are correct and 2 and 3 are incorrect. So which is option D. Okay, question 16, similar type of question, 4 statements. So the first statement is the fiber in the reinforced concrete act as an elongated aggregates. Statement 2 is fiber in the concrete helps to improve the flexural load carrying capacity of the matrix. Statement 3 is the steel reinforcement can enhance all the properties of the cement matrix. Statement 4 is optimum dosage of fiber content in concrete can act as a substitute for reinforcement. So which of the above statements are true? So the options are 1 and 2, 2 and 4, 2 and 3 and 1 and 4. So we have one vote for A, two for B and one for C. Okay, the right option is option A. Statements 1 and 2 are only correct. Okay, so statement 1 says the fibers in the reinforced concrete can act as elongated aggregates. So this is true. So the fibers, so we saw that it is like in the reality they are not long and unidirectional, right? So they will be short and randomly oriented. So this is similar to what we have like elongated aggregates because when you compare the thickness of these fibers to the length of the fibers, so you'll have they'll be longer than they are thicker. So this is similar to what we have as elongated aggregates. So elongated aggregates also have longer length than the thickness or the depth, right? So therefore this is they will be similar, acting similar to having an elongated aggregate in your concrete. So because of their aspect ratio. So statement 1 is true. Statement 2 says fiber in the concrete helps to improve the flexural load carrying capacity of the matrix. So this is also true. So we saw that they have higher modulus of elasticity, right? Therefore your modulus of elasticity of your concrete will also improve, and you can relate that to your flexural load carrying capacity, so that will also improve, right? So therefore statement 2 is also true. And statement 3 says steel reinforcement can enhance all the properties of the cement matrix. So that is incorrect. Some properties will be improved, like your intention, it can help improve your tensile resistance against tensile load, right? So because steel is good in tension, so it can improve that property. Not all properties can be improved just by having steel reinforcement, right? So for example, if you talk about thermal conductivity, it's not just dependent upon your reinforcement. It also depends on your porosity, the type of aggregate that you have, and so on, right? So therefore, just having steel reinforcement cannot magically improve all your properties of the cement matrix. Therefore, the third statement is incorrect. Statement 4 is optimum dosage of the fiber content in concrete can act as a substitute for reinforcement. So this is also incorrect, because having a fiber content, it will improve your load carrying capacity for under flexure, right? Flexural load carrying capacity, but not for your tensile load. Right, so under tension, it cannot improve your tensile load carrying capacity. So that's why we need steel reinforcements, right? So it cannot be a replacement for your steel reinforcement. You still need rebars, all right, but it will definitely improve your flexural load carrying capacity, right? So having fiber content is not a replacement for reinforcement, right? So therefore statement 4 is also incorrect. So out of the four, only 1 and 2 are correct. Therefore the right option is option A. Okay, moving on to question number 17. Lightweight concrete may be produced by, options are lightweight aggregate, incorporating air bubbles in concrete, omitting sand fraction. Option D, all the above. Okay, we have all four votes for option D, all the above. Okay, so the right option is also option D. It is all the above. So all the three given options are perfectly valid when you want to create lightweight concrete. So one is like having lightweight aggregates. So definitely it will help you in producing lightweight concrete. So incorporating air bubbles. So you're introducing voids, right? So therefore your overall weight of your concrete per unit volume weight will also come down by having air bubbles. So omitting the sand fraction, again this will also lead to creating voids, right? So when you have sand fraction, this will improve your packing density. By omitting it, you are introducing again voids. So again that will help you reduce your weight of the concrete. So all these three options are valid options which help you produce lightweight concrete, right? So therefore the right option is D, all the above. Okay, question 18. So we have two statements. Statement 1 says latex modified concrete is an example of polymer concrete composite. Statement 2 is latex after coagulation behaves like rubber. So we have to pick one of the four options. That statement 1 is correct, statement 2 is incorrect. Statement 1 is incorrect, statement 2 is correct. C is both the statements are correct, and D is both the statements are incorrect. Okay, we have three votes so far for option C. Any other answer? Okay, we have four votes all for option C. So the correct option is option C, that both the statement 1 and statement 2 are correct statements. Right, so here we are talking about polymer concrete composite. So we looked at different examples. Right? This was also one of the special types, right, that we discussed, in the fourth lecture. So one such example that we looked at was the material latex, right? So this is one example. So where this is an emulsion, so which means it's some so like ultra fine emulsion, so it will be suspended in a solution, right? So in that case, what happens, after coagulation, which means that it will come together, right? So it will come together and then it will form bigger particles, right? So that's what coagulation is. So it will do that and then it will behave like a rubber. So that's how this material behaves. And this is one such material that we can use for creating the polymer concrete composite, right? So this is what we saw, and that's what is given in the two statements as well. So one says that latex is one example for polymer composite concrete, so that is true. And statement 2 is that once it coagulates, it will behave like rubber, so that's how it behaves. So that is also true, so that both the statements are correct. So therefore the right option is C. Okay, question 19 is, we are given with three types of concrete and three different applications. So we want to match which type of concrete is used for which application. So the type of concretes are heavy concrete, self-compacting concrete, and lightweight concrete. And the three applications are partition walls, shielding material for nuclear reactor, and floors and slabs. So the matches are 1A, 2B, 3C, 1B, 2C, 3A, 1B, 2A, 3C, and 1C, 2A, and 3B. Okay, we have three votes for option B and one for option C. Okay, the right option is option B. One is matched with A, two is matched with C, and three with A. Right, so heavy concrete. So we already saw this application, right? So heavy concrete is used for as a shielding material for nuclear reactors, right? So we saw this application before. And two, self-compacting concrete is used for floors and slabs, because self-compaction is better, will give you a better compaction and better strength than your the regular concrete. So therefore it is suitable for building floors and slabs. And three, lightweight concrete is suitable for partition walls, because your partition walls is not it is not going to carry load, right? So it's not your load carrying, it's not a load carrying component. So therefore in that case we do not need the regular concrete. So lightweight concrete would suffice. So it has lower strength and that is sufficient, because in your partition walls you're not going to carry you're not going to transfer loads, right? So therefore that is suitable for partition walls, and therefore the right matching is 1 with B, 2 with C, and 3 with A, and that is given in option B. Right? So therefore the right option is B. Okay, question number 20 is which of the following material has the highest embodied energy in a typical building? So the options are masonry, plastics, concrete, and steel. Okay, we have four votes all for option C, concrete. Okay, the right option is also option C, it is concrete. Right, so we are talking about the material with the highest embodied energy in a typical building. So what is embodied energy? So embodied energy is nothing but the total energy that that was consumed in the production as well as the transportation of the material, right? So which has this highest embodied energy. So if you look at the different materials, so in a typical building, so this highest embodied energy, when you want to know that, so you want to also know, so what is the highest embodied energy for the for a unit volume, and also what is the total volume of the material in the building. So if you look at it, so we already saw that cement is or concrete is one of the material with the highest embodied energy, right? So for production also it requires higher energy, and also energy is involved in transportation of concrete, right? So therefore it has one of the highest embodied energies. And also if you look at the volumes, if you compare the volume of masonry, that is used plastics, concrete and steel, then concrete is has the highest volume. By volume also it is more in a building, right? So therefore the total embodied energy of the concrete material is the highest when you look at all these four different materials in a typical building, right? So therefore the right option is C, it is concrete. Okay, so do you have any questions, any doubts? Okay, if not, this was the last question for this week. Okay, and also this is the last session that we will have for the week 12, right? So with that, we have covered all the modules that were covered in the course. Okay, I hope that you found these sessions helpful, in preparing for your exam and also in, attending the assignments. Okay, so with that, we come to the end of these live interactive sessions. So if you have any questions or doubts, you can ask. Otherwise, I wish you all the best for your final exam. And so before you leave, I would like to know if you found these sessions helpful, or what you liked or what you didn't like, or if you have any suggestions for improving this, these sessions in the future, you can also let me know that. You can use the chat or you can unmute yourself and then answer. So what did you like or didn't like? Or if you have any suggestions, also you can leave. It will be helpful for me in improving these sessions in the future. Yeah, in your final exam also you can expect similar kind of questions. Yeah, or if you have any other specific questions or doubts also you can ask. Okay, it's helpful. Yeah, good to hear that. All right, so there is nothing else. Feel free to log out. So again, I wish you all the best for your exams. Thank you for attending.